chemistry time, we're going to talk about molecular structures and polarity. So write this down. First we're going to start with molecular structures. Molecular structures. We're also going to talk a little bit about molecular shapes. So for molecular structures, this tells us, this is kind of a simplified version of the way that these molecules would look in real life. There's a picture of this on page 253 if you could turn there with me. They have 5 different little ways of expressing what is here in the book. So if you can see on page 253, there's the molecular formula, right, which was for this one is just pH3. Let's name this thing real quick. What is this called? So we have a formula, pH3. Its name is phosphorus trihydride. So we have its formula, its name. They have here a ball and stick model, and they have a space filling model. What do you think the blue things represent in both of those on this diagram? Hydrogens, yep. And then the kind of mauve thing in the middle? The phosphorus, okay? And then you can't see them in the space filling model, that's why it's called that. But in the ball and stick model, what do you think those white pillars represent?
Like,
bonds, yeah, they're the covalent bonds. Right, and so all the structural formula is that we do, the structural formula looks like this, where we show the bonds as lines. That's it. That's all it is. It's the symbol of the elements attached with lines to each other, right? And the single line here represents a single covalent bond. This is called the structural formula. And why would I even call that? Formula. It's showing the what of the molecule? The structure. That's why it's called the structural formula. And then we also have something that's shown there called the Lewis structure. You might remember that when we did electron dot diagrams, we sometimes called those Lewis dot diagrams. For some reason, this guy Lewis, we named these things after, but this is called a Lewis structure. So the difference between the Lewis structure and the structural formula is what? The Lewis one, they neither one shows how many valence electrons they have, but the Lewis structure also shows this little thing here is called an unbonded pair. Usually it's just called an unbonded pair, but an unbonded pair of what? Electrons, right? Unbonded pair of electrons. So let's do this one next. This is going to be another example. So I'm going to write down the formula for you, and you're going to tell me the other 3 things. So first of all, what's the name of this? Water. Can we also call it dihydrogen monoxide? What? No, we can't call it that. That's wrong. We call it water and only water. Water. Okay, what's its structural formula going to look like?
You put O in the middle, and then off to the side you have a line H, and then on the other side line H.
Yep, and you don't know this yet, but we're going to have to draw them at an angle because for the structural formula, that's fine. But we also have these unbonded pairs. And how do we know that oxygen has unbonded pairs of electrons? Well, first of all, what does each of these lines represent? We already said it's like a bond. Specifically, one line represents a single bond. You remember from, I guess it was weeks ago now, but you remember from the lesson that we did on covalent bonding the first time, how many electrons are involved here in this single bond?
Wait, say it again.
How many electrons are there being shared in this single bond? 2. A single bond is 2 electrons, right? Hydrogen is sharing 1 electron, and oxygen is sharing 1 electron, right? So altogether, how many electrons does this hydrogen have? 2, right? It's sharing 1 from oxygen and it has 1 of its own. We can think of it that way. It's sharing 2. Hydrogen, this one has 2. The oxygen altogether must have, altogether, because it's bonded, so it has 8. It's satisfied its octet. And so we know it's got 2 here and 2 here, so it must have 2 more pairs, and that's what we draw here. And this is getting into something that we're going to talk about, well, I guess we might as well talk about it now. This idea of the Vesper sorry, it's VSEPR, not VSPER. We call this the Vesper Model. And what this is short for is valence shell electron pair repulsion. We'll break that down in a second, but for now just write it down. Vesper stands for valence shell electron pair repulsion. It's a model of the way that molecules work. Did we talk about what, when I say molecule, what does that mean? We should talk about that in a second, but well, we should probably talk about it now. Molecular, this means that it has to be covalently bonded. Write that somewhere in the margins or somewhere where you won't forget it. When we talk about a molecule, that has to be covalently bonded. It must be. So sodium chloride doesn't count as a molecule because it's not covalently bonded. Once again, how do we tell if something's covalently bonded?
If it's bonded between a non-metal and a non-metal.
Yeah, if it's non-metals, two or more non-metals bonded together form, we call it a covalent bond. We also call it a molecule, right? And we sometimes even call that type of bonding. You will hear covalent bonding called molecular bonding a lot. You might write that down too. Molecular bonding equals covalent bonding. They mean the same thing. That might help you remember also that only covalently bonded substances are molecules.
And that's two or more
Non-metals bonded together. So anyway, we have this valence shell electron pair repulsion model, which shows us the way that the shapes of molecules form. And I did say molecules, right? That means they have to be covalently bonded. And what it basically means is that for every pair of electrons, they're getting into some quantum mechanical kind of nonsense about why they stay as pairs. But basically, each pair of electrons, whether it's bonded or not, wants to be as far from the other pairs as it possibly can. So write that down. Each pair of electrons, specifically valence electrons, I'm going to write that in. Each pair of valence electrons, I shouldn't say once, is repelled to be as far from the other pairs as it can. So they stay as far away from each other as they possibly can, but still being in the same shell. And that's why we get these shapes. So if I was going to draw this very accurately on my water, I would make sure that there's the same distance between the bonding with the hydrogen as this lone pair with this lone pair, and this lone pair with the other hydrogen bond. They stay as far apart as they possibly can. Why? Say it.
Electromagnetic force?
Yeah, the electromagnetic force, except in this case, instead of an electromagnetic attraction between a positive and negative, we have a what? A repulsion, because they're all negative. All these electrons are negative, and so they stay as far away from each other as they can. Kind of in the same way, and it's the same force as when you have the south poles of two magnets. They won't touch. They try to stay as far away from each other as they can, but they against the other forces, right?
You can kind of make them, can't you?
Yeah, you can press them together, but it takes more force, right? And then if you let them go, they'll push apart until they're as far away as they need to be stable. It might be easier, as I was doing this one to show you, it might be easier if you do the Lewis structure first, because that can help you figure out how far away to make them from each other. Like if we'd done this one first, you might be tempted just to make it be hydrogen, hydrogen on either side, right? Let's do this one. Name? Carbon dioxide. Carbon dioxide. So what's probably going to go in the middle?
C. And then slightly
Now,
on top.
and be kind of careful, because how many valence electrons does carbon have? Look at the periodic table.
Carbon
4. And how many does each oxygen have? 6. So, how many bonds is the oxygen going to have to be happy? 2 bonds, right? And the other oxygen is going to also have 2 bonds, which will give the carbon 4 bonds, right? Which will make it happy. So these are both going to be what kind of bond then? What do we call it when it bonds with 4 electrons? 2 bonds. Yeah, it's still covalent, but a double covalent bond, right? So we're going to have these two double covalent bonds. And that's what this is. This is how we indicate a double covalent bond. And now, unlike our water, the carbon has no unbonded pairs, and so these already are as far apart as they can get just by being straight out. The oxygens still each have two unbonded pairs. So that's the Lewis structure. So now how many electrons does this have altogether? 1, 2, 3, 4, 5, 6, 7, 8. Sorry. Remember, each one of these bonds has how many electrons? 2. Each bond is 2 electrons. So the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. They're all perfectly happy, right, with these double bonds. Does that make sense?
So how do you know when to do a double bond?
So, because what would happen, excellent question, what would happen if we tried to make these single bonded is that none of them would be satisfied, right? And we know from the fact that this exists that they must be satisfied. So you just kind of, I mean, you can, there are methods that your book gives on how to do it like as rules of thumb, but basically it amounts to just trial and error, right?
Okay, so just if you do it and you...
And it doesn't work out,
okay.
Then do it again and make it work
and
out.
And if carbon dioxide is on the... Just memorize that that's...
Yeah, and there's I wouldn't worry too much about these yet. You'll do these probably a lot more when you get to college chemistry, but for now I just want to give you a rundown of this so that you understand basically what a structural formula is. You won't have to make your own, and if you do, I'll be pretty lenient with them, but you want to make your own, but I do want you to know the difference between what a structural formula is and what a Lewis structure is. So this, sorry, go ahead.
You don't necessarily have to know how to do it.
Right, but you need to be able to recognize it and like be able to tell what each of these things means. But this is the Lewis structure, so what's the structural formula going to look like?
Like that right there.
Carbon.
Same thing, except no what? No unbonded pairs. We don't show the unbonded pairs.
You just show... You don't show
Right. Okay, now look with me. There's a chart on page 263 I want to draw your attention to. This is a table of the molecular shapes. Let's try to name some of these. And you don't have to have this table memorized. I just want you to be familiar. Like you are familiar with this, I want you to be familiar with what some of the names of the shapes are. So what would we call this one, looking at it? Of all those on there, kind of glance over this for a second. What would we call carbon dioxide?
Linear?
Yeah, it's linear. It forms a line. Do you remember in one of our videos, Professor Martin Polyakov was telling us about beryllium chloride? That's the example the book is using as a linear one, too. Beryllium chloride there. What would we call this one?
That's either
Trigonal pyramidal, maybe is what you're trying to say? Or maybe you're trying to say trigonal planar?
Yeah.
But watch out, because it's only got 2 little things coming off of it. We don't count the unbonded pairs. What did you say? Say it again. Bent. Water is bent. In fact, the example in the book is water, and it's bent. What about this one?
Who's that?
Would that be...
The pH3.
Would that be the
Trigonal is how the word's pronounced. Trigonal. Not trigonal planar. Try again. Trigonal pyramidal. Trigonal pyramidal. I want you to be kind of familiar. You don't have to have these memorized. I want you to be aware that there are names for these shapes. Pretty much that's the end of the story. You might be called on to tell whether something is linear, not given an example, or whether it's bent, but those are the 2 most basic ones. Let's move on to polarity. So do you have questions about molecular structures and shapes before we go on? The main thing is, could you recognize these structures, yes or no? Like, can you tell the difference between a structural formula and a Lewis structure? Probably. And you need to know about Vesper and why it occurs, right? And basically, it occurs because they repel because of the electromagnetic force, right? So you need to know about Vesper. We're just going to erase this real quick. And now write down the next part of our notes is going to be called polarity. Did I say that word clear enough? Polarity. Polarity, meaning it has what? Poles. Polarity. Whoops. marker. Polarity. And this word just means that it has poles. Molecules that have a slightly positive and slightly negative end are called polar molecules. Because they have what? Poles. Because they have poles, right? They have a positive pole and a negative pole. What's sometimes called a dipole. What's di mean? Two. Yeah, because they have two poles. There's a chart. This exists on the internet too. If you type in electronegativity chart, it's in your book on page 265, but it's also on all over the internet. And it, for each of the elements, it's a periodic table. You might even bookmark this. We come back to this a lot. But this electronegativity chart, each of them has three things on it. It has the atomic number, so you can find it more easily. This one has the atomic symbol. They come with names too, but this one has the atomic symbol. And then it has, what's that little bottom number? Let's read together the caption, please, Tylee. Let's read the caption together. It says, electronegativity values are derived by comparing an atom's attraction for shared electrons to that of a fluorine's atom attraction for shared electrons. Note that the electronegativity values for the lanthanide and aconite series, which are not shown, range from 1.12 to 1.7. Doesn't matter. But that bottom number on this chart, you see that bottom number? Underneath each element. So it has atomic symbol, and then under the atomic symbol is what we call the electronegativity. All these are compared to fluorines. What's fluorine's electronegativity? 3.98. It's almost 4. Fluorine, you should write. Fluorine is the most electronegative, and we'll define that word in a second. Fluorine is the most electronegative, sorry, that's not the word. Fluorine is the most electronegative element. Given what you already know about fluorine, what does that probably mean?
It means that the higher, the more negative.
Yeah, so how many valence electrons does fluorine have? 7. How many does it want? 8. So it really, really, really wants what? One more electron, right? That's what electronegativity is. Fluorine is the element that wants another electron the most. Fluorine is the most electronegative element, and electronegative is just a word that means how badly it wants another electron. Fluorine is the most electronegative element. I'm tentative to put how badly it wants another electron, but let's just put most attracted to other electrons, right? It really wants 2 electrons. We'll just put 2 electrons. Most attracted to electrons. It really wants another electron. Which of those, if you had to guess, look where fluorine is, and then tell me which of them would you guess is the least electronegative? And verify it with your chart. The noble gases aren't even shown because they don't have one. Yeah, they are the least electronegative. Of the elements that have an electronegative, good point, Hayes. That's not what I was looking for, but you were right.
The FR, which is...
Yep, it is FR, which is francium. Francium has the lowest electronegativity. And what does that mean?
It means that
it does not want another. It does not want another electron at all. How many does it have? It wants to get rid of one so bad. It does not want another one. FR is right here. So top right of this chart, remember it doesn't include the noble gases. Top right wants an electron the worst. It needs another electron. Bottom left doesn't want it at all. It would much rather give up the electron it already has. And so generally, as we go right, what happens? As we go right on the periodic table, what happens to electronegativity?
It goes up.
Goes up. As we go down, it goes down. Good.
So why does hydrogen have that? It has like a 2.
Yeah, so hydrogen is, because remember, hydrogen, while hydrogen only has one electron, how many does it want? It only wants two. So it'd be just as happy, remember, it'd be just as stable gaining one more as it would losing its first one. Good question. Look, now turn the page. There's a little electronegativity difference. It abbreviates that as EN. But electronegativity difference and bond character. So what we do is we find the electronegativity of both, or a bond can only happen between two atoms, right? So for a given bond, find the difference in electronegativities. I abbreviate that also, EN, electronegativities, to determine what's called the bond character. Your character is just how you are, right? Your character is sassy or happy or gloomy or whatever. That's what your character is. When we talk about the bond character, that's just how the bond is, what kind of bond it is. So look at these differences here. If we calculate the difference, if we subtract the small one from the large one, and we find that it is greater than 1.7, we call that ionic. If it's between 0.4 to 1.7, we call that polar covalent. And if it's, I'm gonna abbreviate this chart, which is already pretty short, but if it's less than 0.4, we call it non-polar.
What was the second one? Polar.
Polar covalent. What's another name for a covalent bond? Do you remember?
Molecule.
Molecular. So we could say polar molecular, but we generally just call it covalent. And then if it's less than 0.4, your book says that's mostly covalent, but that gets into a definition of covalent that I don't want to use.
Non-polar.
And we call it non-polar covalent, basically. If it's smaller than 0.4, we call it non-polar. So an example is given there on page 267. So the next page, it's the hydrogen chloride particle. So what they've done is they've taken chlorine's electronegativity, 3.16, subtracted hydrogen's electronegativity, 2.20, and found it to be 0.96. So where on our scale here is 0.96?
It would be great.
It would be a polar covalent.
Polar covalent. So that's a molecule, but it's polar. And what does polar mean? Well, that's the last thing we're going to talk about today. Well, I guess we probably have two more things, but basically it's this. A polar molecule is one, like we said, that has a slightly negative end and a slightly positive end. The classic example of this is water. So draw a little water molecule here. Why did he draw it with the two hydrogens way up in there? Why is that? Because there's two unbonded pairs down here that we're not going to show. But it is kind of important that we understand those two there, because basically what happens is this. Where do the electrons, remember the electrons are always moving, where do they like to spend most of their time? If you were an electron, which would you be more attracted to, the oxygen or the hydrogen? Oxygen. And why?
Because it has a negative charge.
It does have a negative charge, but that's not why. What are the electrons attracted to about an atom?
You can get rid of your electron.
You're just an electron. You're just a single electron. What are you attracted to about these atoms? What part of the atom attracts you? The nucleus. So basically, which one's got the larger nucleus, right? Attracts you more. So here, the oxygen is more attractive to electrons than the hydrogens are. So they spend more time down here, the electrons do, spend more time around the oxygen, giving it what we call a partial negative charge, because there's more electrons, right? And we indicate that with this little symbol. It's called, this is the lowercase Greek letter delta. Lowercase, what's the capital Greek letter delta look like? You remember?
It's like the...
Capital delta is a triangle. Doesn't matter right now. But this little squiggle, you can look in the book, because everyone always gets really mean to me about how I draw it. But look in your book. It's there above the hydrogen chloride bond. This is the lowercase Greek letter delta. And we use that to indicate this is a partial negative charge. And if this end has a partial negative charge, what's this end probably got?
Partial
partial positive. So basically what happens is, because of the way the electrons like to spend their time, one end gets kind of a negative charge and one end gets kind of a positive charge. And this is called polar covalent bond. It has poles, right? It's polar. A polar bear lives on the poles, right? Polar is the adjective we use to describe something that has poles. And this is important because water has this, what we call a dipole, right? It has a difference between its positive and negative end in electronegativity. And because it has this dipole, like, some of the properties of water that are the most important are because of this. So like, when you pour salt into water, it dissolves because the sodium chloride, let me just draw it up here. We have sodium chloride, right, which is ionic. Sodium chloride, they're held together by the ionic bond, right? Made of a sodium ion and a chlorine ion. The chlorine is attracted to this end of that water, and the sodium is attracted to the other end. And so basically, when you pour salt into water, the reason it seems to disappear is because the water is physically ripping apart the bond that holds the sodium and the chlorine together, and these guys are going to hang out with the water instead. Does that make sense? So when something dissolves, it's because this bond, the ionic bond between these, is being broken, and it's because of the water's charge. Does that make any sense to you at all?
Yeah.
Do you have questions about this? This is I understand this is kind of a whatever. Guess I'm done.
Videotape this?
Yeah, it's being videotaped. Do you have a question about this though?
No.
So it's polar because of where the electrons hang out, and the reason it's important is because of some of the properties it has, like it can dissolve ionic substances. Remember back when we talked about ionic substances, one of the things we said is that they dissolve in water. And it's because of this. Can you calculate whether something's going to be polar or nonpolar? Sure you can, right? That's what we just did. Questions? Okay, you have your assignment.